In the last episode, we finished talking about the details of a seemingly failed experiment. The experimenters turned it into a working experiment by meticulous troubleshooting using negative controls and flexible, deep thoughts. In my view, the lessons learned from a failed experiment are hidden gems. We will talk about those lessons today. This episode is part 1 of the 2-part reflections on the story. Hi everyone, welcome to the Foundational Skills in Life Sciences podcast. I'm your host, Dr. Synaptologica. We discuss the skills that life science scholars learn, use, and improve throughout professional activities. Your benefit is expressed in my motto, learn the skills, enjoy academic life. Last episodes. From the episode number 19, we have been discussing a real story about a life science experiment. It was one specific pilot experiment that did not work well at first. And we finished discussing the core parts of the story in the last episode, episode 24. We spent a total of 5 episodes to discuss it. I hope you're feeling happy as I am, because we could follow a course of deep thinking processes. It was a rare learning opportunity for us because those thought processes are usually hidden when we read scientific papers. In a way, it was like reading between the lines of a paper, uncovering the thought processes behind the results. Today's episode. The goal of today's episode is to learn lessons from the story. We can learn a lot from any troubleshooting experiments because troubleshooting experiments can reveal our mistakes, they can uncover hidden scientific facts, and they can sometimes open up new types of experiments. Our story about the failed pilot experiment was very insightful. Our story is rich with lessons. Today's episode is part 1 of 2-part reflections on those lessons. We will focus on lessons related to negative controls. In the next episode, which is part 2, we will focus more on general lessons beyond negative controls. Now, before talking about the lessons, let's quickly review the original problem in the pilot experiment and what caused the problem. The original problem. The experimenters were trying to test if an active form of a specific chemical compound stimulates cultured cells so that their function would increase. For this purpose, they prepared a positive control and a negative control. In a positive control, the active form of the compound was expected to increase the function. In a negative control, the inactive form of the same compound was expected not to increase the function. The problem was that the treatments with active or inactive form led to the same functional level. In other words, the positive and negative controls were indistinguishable. Because there was no difference, the logical conclusion was that the active compound did not increase the cell function, in contrast to their expectation. The cause of the problem that the experimenters figured out. To solve the problem, the experimenters carefully designed and performed troubleshooting experiments. Through 4 such experiments, they figured out what caused the problem in the original experiment. Here's what happened in the experiment in retrospect. I will describe it in 5 steps. 1. In the early part of the experimental protocol, the old culture medium was replaced with the fresh medium. The old culture medium contained an important component, the animal serum, but the fresh medium did not. So when the culture media were exchanged, serum was effectively removed from the culture medium unexpectedly and unintentionally. 2. This serum removal somehow stimulated the specific cell function that they were looking at. 3. The stimulation started soon after the serum removal. 4. Moreover, the cell function was maximally stimulated, reaching saturation. And the stimulated state lasted until the end of the experiment, when a chemical compound was applied to the cells and the cell function was measured. So the function was already high and saturated, even before chemical applications, irrespective of whether the chemical compound was active or inactive. There was no room left at all for an active compound to induce any further response. And 5, this was the reason why there was no difference in the cell function between the positive control treated with the active form of the compound and the mock treatment negative control treated with the inactive form. So the root cause of the problem was that the serum was present in the old culture medium, but the serum was absent in the fresh culture medium. Medium exchange removed serum from the fresh culture medium, and it stimulated the specific cell function. I would say that the experimenters clarified the pathophysiology of the problem. After understanding the problem, they could refine and update the protocol. In the new protocol, the serum was included in all the media throughout the entire experiment at the same concentration. Comment 1. Remaining questions. Before talking about the lessons we learned, I would like to point out one more thing. The experimenters successfully identified a problem and solved the problem, but I'm sure you had some questions when you heard the story. For example, 4 questions quickly come to my mind. 1. Why does a cell function change when the serum is removed from culture medium? 2. Do any other functions change in addition to the specific function that the experimenters were looking at? 3. Will any other cell types be affected the same way in addition to the specific cell type that the experimenters were working on? And 4. Which condition is more physiological, culturing cells with serum or without serum? The experimenters did not know the answers to any of these questions, but they felt satisfied with the progress at the time, and they were able to move on to do more experiments using the upgraded experimental protocol. It was a real story, but I wanted to make the story more generally applicable to you, even if you work in a field different from that field of the experimenters in the story. This is the reason why I did not specify the details of the experiment. For example, which type of cells were used and which specific cell function was measured and how it was measured. Now, back to the main content. Lessons that we can learn from the story. We can learn multiple lessons from this story. Today we are going to talk about the first 3 lessons. They will be related to negative controls of experiments. Lesson 1. Importance of negative controls in life science experiments. First of all, let me say that in our story, we have seen the power of negative controls in life science experiments. We would agree that any experiment needs a negative control, but we have seen more than that in our story. The experimenters prepared multiple types of negative controls, and they took full advantage of all negative controls. Let's briefly see how they proceeded. They obtained the initial data in the pilot experiment. The data were problematic because there was no difference in the results between the positive and negative controls. The experimenters came up with a hypothesis, that is, idea 1, to solve the problem. They devised a new negative control to test this idea 1. They performed troubleshooting experiment 1, and they obtained data which were still problematic. The experimenters came up with a new hypothesis, that is, idea 2, to solve the problem. They devised a new negative control to test this idea 2. They performed troubleshooting experiment 2, and they obtained data which were still problematic. They kept repeating this process, and they solved the problem with the updated idea 4 and a new negative control in the troubleshooting experiment 4. So the experimenters used negative controls for at least 4 purposes. 1. Evaluating whether an entire experimental system works well or not in the first place. 2. Surveying the details of experimental protocol for detecting a potential problem in an experimental design. 3. Providing data for experimenters to come up with ideas for solving the problem. And 4. confirming that the problem is solved and the troubleshooting is completed. I would like to emphasize the importance of negative controls. Of course, negative controls will work always with positive control counterparts. But some people might think that only positive controls are meaningful and negative controls are not important. Some could even claim that negative controls are boring. I do not think so. Our story about thoughtful experimenters told us a lesson. Lesson 1 is that negative controls are meaningful and important, like positive controls are. Lesson 2. Assumptions of negative controls. In episodes number 18 and 19, we talked about 2 assumptions of negative controls. Negative controls will work well when either of these assumption 1 or assumption 2 is satisfied. Just a brief note, I forgot to mention there that the assumptions 1 and 2 are my statements. Let's review them here. Assumption 1 says that when the measured value of a negative control is almost 0 and very different from the values of the positive control or the test groups, the negative controls might work well so that the measured values of the positive control or test groups might be accepted as they are. Assumption 2 says that when the measured value of a negative control is a large, non-zero value and occupies a large fraction of the values of the positive control or the test groups, the negative control will work if the measurements of the positive controls and the test groups are independent of the measurements of the negative control. These statements will apply to negative controls in general. The negative controls include both a no-treatment negative control and a mock-treatment negative control. Just as a reminder, in no-treatment negative controls, there are no specific treatments, like applications of chemical compounds. So they do not strictly compare with a positive control, which will receive a specific treatment. In mock-treatment negative controls, there will be specific treatments, like applications of an inactive form of a chemical compound. So they are symmetric with positive controls. They are closer in condition to positive controls than no-treatment negative controls. But why are we discussing the assumptions behind negative controls here as a lesson? This is because the assumptions are deeply related to the core of analyzing data, and the assumption 2 was not satisfied by the original negative control in our story. In fact, I decided to introduce our story into our episodes because it was an excellent example where a negative control did not satisfy the assumption 2. When the assumption is not satisfied, experiments will generate misleading results. In our story, when the serum was removed, it stimulated both the negative control and the positive control to the same maximal degree up to the saturation. Then they were treated with inactive and active forms of a chemical compound. This means 2 things. 1, the negative control gave a large, non-zero value of cell function. The assumption 1 will not apply here because the assumption 1 applies to a negative control that gives almost a 0 measurement value, very different from the values of the positive control. So our story was the case for the assumption 2. Then assumption 2 needs to be satisfied. But 2, assumption 2 was not satisfied. This was because the measurement of the positive control is not independent of the measurement of the negative control. In fact, they were the same. 100% of the positive control was represented by the negative control. Here is the critical viewpoint. This situation happened because both the serum removal and the active chemical compound activated the same signaling pathway that led to the same functional change. So the negative control and the positive control were identical. They were not independent of each other. So this story is a perfect example of the situation where assumption 2 does not hold. The experiment's hidden issue was that removing serum stimulated the cells in both the positive and negative controls, leading to the same functional response. This was not apparent to the experimenters initially. But if they had been aware of the assumption too about negative controls, it could have given them some cause for doubt from the start, and it could have helped them earlier in the troubleshooting process. I hope the assumptions will serve you as a clear reminder to carefully think about what is happening behind your measurements and your experimental conditions. Lesson 2 is that the assumptions of negative controls are critical in determining whether negative controls work well or not. Here, I would like to give you 3 comments 2 through 4, about some principles among biological systems. Comment 2, dose-response relationship and another scenario. One comment is about a relationship between the degrees of input and output. It is called a dose-response relationship or a concentration-response relationship if a chemical is applied at different dosages or concentrations. Or it can be called a stimulus-response relationship if a non-chemical stimulus is applied at different strengths. A common principle would say that when an input is weak, the output response is weak. When the input becomes stronger, the output becomes stronger. And as the input is made even stronger, the output will reach saturation. The saturated level is like an unbreakable ceiling. Even if the input is made stronger, the output cannot go above that level. This behavior is typically seen with a dose-response relationship, where a chemical binds its receptor and the binding triggers a response. Let's visualize the response as a graph. The x-axis represents the degree of input or the amount of dosage. The higher the x-axis value, the stronger the input. That is, the more to the right of the graph, the stronger the input. The y-axis represents the degree of output or the amount of response. The higher the y-axis value, the stronger the output. Now, when the input is absent or very weak, there is no output. So the left side of the graph, which corresponds to weak inputs, shows no output. As the input becomes stronger, there appears a stronger output. So the middle of the graph, which corresponds to the middle degree of inputs, shows some output. When the input becomes strong enough, the output reaches saturation. Stronger input than this maximal input will only lead to the same saturated level. So the right side of the graph, which corresponds to strong inputs, is high and remains high to the rightmost part of the graph. This graph is shaped in a deformed letter S, so it is often called the S-shaped curve, sigmoid curve, or sigmoidal curve. The experiment in our story behaved this way. There was a clear saturated level. Serum removal caused a maximal stimulation, and further addition of an active chemical compound could not increase the cell response further. I would like to add that this is not the only principle in biology. There are other different principles. One example is represented by a so-called bell-shaped curve rather than a sigmoid curve. Let's visualize the response curve. The x and y axes are the same as in the sigmoid curve. They represent the degree of input and the degree of output, respectively. When the input is absent or very weak, there is no output, as in the sigmoid curve. As the input becomes stronger, there appears a stronger output. As the input becomes stronger still, at some input point, the output reaches a peak value. The maximal output is obtained. When the input becomes even stronger, the output decreases. So overall, the left side of the graph is low, the middle part is high, and the right side becomes low again. We have been talking about a dose-response relationship. Along the same line, let's stretch our imagination in an intellectual exercise. we will consider a hypothetical scenario in our story. The result could have looked very, very strange in this thought experiment. Let's say that the serum removal stimulated the cell function maximally, as in our story. The serum removal corresponds to the negative control, as in our story. But let's also say that the cell function follows a bell-shaped curve instead of a sigmoid curve. This is different from our story. When an active compound is applied to the cells after serum removal, it could lead to a weaker cell function, following the downward trend on the right side of the bell-shaped curve. So the function in a negative control is high, whereas the function in a positive control would be low. This result will look very strange, but it will make sense if we understand the hidden biological principle behind the experimental data. Comment 3. Still another scenario. In this comment, I would like to say that the experimenters in our story were lucky in a way. They were able to find and solve a significant problem because the cell function was stimulated maximally, that is 100%, by the serum removal. As we have seen, this led to the same level of function reported by the positive and negative controls. This was the original problem, and the problem was clear to the experimenters. But let's consider another thought experiment. In another scenario, let's suppose that the cell function was stimulated less than 100% by the serum removal. Let's say 50%. The experiment under this scenario might look similar superficially to some people, but if we think carefully, it will lead to a totally different result. Under this situation, the negative control will show 50% of the maximum cell function because the negative control experienced only serum removal. The positive control will show 100% of the cell function because it will be stimulated with a maximal concentration of the active chemical compound later, after serum removal. So the positive control shows higher function than the negative control. This result seems good. So the experimenters could have missed the serum removal problem in the first place if the serum removal stimulated the function only partially. But the partial stimulation could lead to a strange result. For example, let's suppose that the goal of the experiment is to evaluate the effects of different concentrations of the active compound on the cell function. This is the dose-response relationship we just talked about. The serum removal has already stimulated the function at 50% level before the active compound is applied to the cells. Then there will be at least two problems. 1. Because of a prior partial stimulation by serum removal, the baseline of cell function becomes high at 50% level. Then there will be less room left for a response to occur between the elevated baseline and the maximal saturated ceiling when the active compound is added as a later stimulus. So the absolute degree of response to the compound will become smaller. 2. More importantly, the shape of the dose-response curve could be changed. It is possible that the active compound at a low concentration would induce no response at all, although it could induce a weak response if there's no partial stimulation by serum removal beforehand. Then only the active compound at a high concentration could be effective in inducing a response. So the dose-response curve would be distorted from the real curve in the absence of stimulation by serum removal. I'm not saying that the result should always be strange when serum removal stimulates the function partially before treating with active compound. I meant that a strange result could happen. But this thought experiment will help us be prepared. It is healthy for us to think that anything unexpected could happen in any experiment. Comment 4. Characteristics of functional changes. I would like to remind you that an impact of cell stimulation can be different in terms of pattern, time course, and interactions. In the experiment of our story, serum removal had a stimulating effect on a specific cell function, and it lasted very long. In other experimental systems, there could be no effect of serum removal at all. In totally other experiments, a stimulating effect of an event, like serum removal, can be short-lived, and it can have no effect on a subsequent event that happens much later. In still other experiments, a stimulating effect of an event can be small in degree, but it could suppress subsequent event drastically, like in the phenomenon called desensitization. I will not go into details here, but it is good to keep in mind that every experimental system will be different. So we want to be careful about the uniqueness of an experimental system when we work on our own. Let's get back to the main content. Lesson 3. Modified definition of negative controls. In our story, the experimenters originally found similar results between the positive control treated with an active compound and the negative control treated with an inactive form of the same compound. This inactive compound was known to serve as a negative control. The experimenters had believed that this negative control should work fine. So the logical conclusion of the original pilot experiment was that the active form in the positive control was not effective in stimulating a cell function. Here the experimenters were lucky again. At first, they did not even think that they would experience a situation where a negative control fails to work. But the experimenters carefully read the papers by other researchers and received information that the active form stimulates the cell function. This information from the other research groups was the trigger for the experimenters to move in the right direction, that is, to question their negative control and to start troubleshooting experiments. If they did not receive valuable information, they would not have suspected that their negative control was not working well, and they would have wrongly accepted the logical but unexpected conclusion that the active compound was ineffective. Let's think about our own situations. We will be lucky if we have access to such valuable information in scientific papers or in oral communications. Then the negative control will be known to work. But a negative control that is known to work in the hands of other research groups does not necessarily work well in our hands. Such a negative control is thought to work, but there's no guarantee that it will work as true negative control. In addition, when we do experiments, such valuable information is, quite often, unavailable. This is especially true when we do an entirely new experiment that nobody has done before. Also, there are situations where we evaluate the experiments performed by other researchers, like when we peer review the manuscripts submitted to scientific journals. We might not have enough time to search for valuable information in scientific papers or in oral communications. Then, how do we stay cautious about blindly accepting that a known negative control should always work in every situation? It is by thinking that a negative control might not work. This is the point. This is the main reason why we modify the definition of negative controls. Please recall that we modified the definition of negative controls in episode 18. Let's review the definitions. A typical definition that we will find is a negative control is a sample where the expected outcome is known to be absent. Our modified definition is a negative control is a sample where the expected outcome is thought to be absent. The modified definition is more practical and realistic. And importantly, the modification will prepare us to be careful, cautious, flexible, and open-minded about multiple aspects of experiments. For example, I'm going to give you 7 aspects of experiments: interpreting data, analyzing unexpected outcomes, identifying a potential problem, understanding what is happening at the deep core of the experimental protocol, solving the problem, improving the protocol, and improving the way we perform experimental protocol. In our story, we have seen that the experimenters used negative controls successfully to address all of the above aspects. Lesson 3 is that a modified definition of negative controls makes us flexible in the thinking process. Our modified definition of negative controls will serve as a strong reminder that any unimaginable factor could contribute to an experimental system, even to the basic negative controls. By the way, our modified definition is my statement too. Summary. We have discussed 3 lessons, all about the negative controls in life science experiments. Lesson 1 was that negative controls are meaningful and important, like positive controls are. Lesson 2 was that the assumptions of negative controls are critical in determining whether negative controls work well or not. And Lesson 3 was that a modified definition of negative controls makes us flexible in the thinking process. In the next episode, we will talk about the lessons beyond negative controls. They will be related to general mindset about doing experiments and interpreting experimental data. This is it for today. Your action. What lessons did you learn from our story? Could you share those lessons with me? Please contact me by email. My email address is ideas@synaptologica.com. Thank you for joining me in today's episode of Foundational Skills in Life Sciences. I'm Dr. Synaptologica. I'll see you soon. Bye for now.